I want to talk today just about a little bit more physics. So this is kind of physics according to Newton. So we already saw this philosophy a little bit in the last lecture, where I proved that the parabola had the property of focusing light. And what we did when we did that was we took the physical laws, in that case how light reflects, so that the angle of incidence equals the angle of reflection, and we turned that into a differential equation for the curve that we were looking for, and then we used the math to solve the differential equation. So this is a totally basic philosophy when you're kind of meshing math and physics together. Physical laws lead to differential equations, and then you do the mathematics to solve those differential equations to get the final solution. Okay, so I have talked just a little bit about Newton's laws of motion before, not very much, but remember we talked about the law F equals ma, force equals mass times acceleration. Let's maybe include the units here. You know, mathematicians usually ignore units, but they're there in the background. So the force is measured in newtons. What a surprise. Mass would be kilograms, and acceleration, that's meters per second squared. Okay, so what did we do with that? Let's just think for a second. With that law, we had, if you remember, I did the example of the apple falling from the tree. So let's measure height downwards for once. So y is the distance it's fallen. So at time 0, y is 0. And you remember that in this case, so if the apple is of mass m, gravity exerts a force, mass times, there's this little constant g, which is the acceleration due to gravity near the Earth's surface, and that led us to the differential equation that y double dot, remember we used dot for time derivative, so this is the second time derivative of y, in other words it's the acceleration, that's equal to that constant g, 9.8 meters per second squared. And then we solved that to get that y dot was gt plus a constant, but because y dot of 0 equals 0, the constant is 0, so let's just ignore that constant. And then we integrated one more time to get that y is a half gt squared plus another constant, but because y of 0 is 0, now I'm doing this, the other constant d is 0 too, so we can just ignore that. And so there's our distance y, distance fallen in time t, is a half gt squared. So let's say it's height h from the ground. Natural thing to ask is, when does the apple hit the ground? So all I have to do is I have to work out what time t is y equal to h. So y is given by this formula, a half gt squared. We want y to equal h. So t is, let me see, 2h over g square rooted. Okay, so that's how long it takes the apple to hit the ground. And then I'm going to ask, what is the velocity of the apple? When that happens. So let me see. So velocity is gt, and we know the time t when it hits the ground. So it's g times that time root 2h over g, which is the same thing, that g comes inside the square root and it's a gh, so it's the same as square root of 2gh when it hits. Okay, so that's the velocity of the apple. That would be in meters per second. Good. So let's come back to these laws of motion. So I've given you F equals ma, force is mass times acceleration. Another useful law is work is force times distance. Sorry, that one I don't have shorthands for those things. That's just in my head. Work equals force times distance. So work here, that's energy. And that's measured in joules. That's the unit for energy. But because work is force times distance, a joule is the same thing as a Newton meter, or a Newton is a kilogram meter per second squared. So a joule is the same thing as kilograms meters squared per second squared. Okay, so those are the SI units that if you've learnt a little physics, you know all about that. But it's not terribly important for us. I just, the units are a good reality check that what you're doing isn't going wrong. So, for example, to raise the apple from the ground to height h takes how many joules? Work. That's the amount of energy we need to put in the apple to lift it off the ground to height h. That amount of energy that we need to put in, work, is force times distance. Okay, so how much force have we got to put in? Well, the gravity pulling down is mg. So to move the apple up, we've got to put in exactly that force to balance off the gravity, right? So we need to put in force mg. So that's the force we need, and the distance we've got to put in force mg for a distance h. Okay, so if you imagine the apple is sitting on the ground and you need to lift it up to height h, you need to put in mgh, joules of energy, to do that. So that's going to be a very important formula, mgh. So that's called PE, potential energy. Okay, so that energy you put in to lift the apple off the ground to height h is mgh. That's a very useful formula. Potential energy is mgh to lift a mass m near the Earth's surface to a height of h. So we're kind of getting to one of the very basic fundamental laws in this sort of Newton's physics, which is all about conservation laws. So the law that we're thinking about is conservation of energy. Okay, so energy is conserved. So when that apple's sitting on the ground, to lift it to height h, you need to put in mgh joules of energy. That energy goes into the apple. So now the apple has mgh joules of potential energy stored in it. You will have done a little bit of work to do that. So you will have burnt a little bit of energy yourself. You will have burnt mgh joules of energy, which will have gone from you into the apple. And then when you let go of the apple at height h, it starts accelerating under gravity. That potential energy turns into kinetic energy as it goes faster and faster. And that instant when it hits the ground, all that potential energy, mgh joules, which it had when it was at the top, has been converted into kinetic energy that instant that it hits the ground. So all mgh joules of potential energy becomes kinetic energy when it hits the ground. Right, so it's then a distance 0 from the ground, so there's no more potential energy in it, but all that energy has gone into kinetic energy. So let's think how much kinetic energy is it. So kinetic energy, let's see if I can do this. So we've got we've got a mass m moving at velocity, so that instant it hits the ground, its velocity v is square root 2gh. How much kinetic energy has it got? Well, it must have mgh, joules of kinetic energy, because that's all the potential energy converted into kinetic energy. So kinetic energy is to do with mass and velocity. So how can we get mgh from the mass and the velocity? Well, that's a half mv squared, because if you plug in, so there's the half, there's the m, if you plug in the value of v, root 2gh, you need v squared. That's 2gh. Oh yeah, that's 2gh. So that's the formula. So I think I've basically just kind of convinced you, hopefully, that the kinetic energy formula is a half mv squared. So that's kinetic energy for mass m moving at velocity v. Okay, so that's another kind of very useful formula, and you kind of see that being kind of justified from this experiment that we've just done. All of that potential energy must have been converted into kinetic energy, and since when the apple lands it's moving at that velocity, that kind of validates this formula for kinetic energy. It makes that work out. mgh, all the initial potential energy has turned into kinetic energy. So, okay, that's the first kind of basic conservation law in physics, conservation of energy, and that's often very useful when you're kind of doing some of these sort of Newtonian dynamics type of problems. So, potential energy, mgh, kinetic energy, a half mv squared. Those are two very useful formulae. I'll come back to Newton's law, F equals ma, a little bit later in the lecture, and talk a little bit more about conservation laws. But let's do another example of a basic physical system that we can understand in these terms. So what I'm going to do is think about another example. So this example, let me see, I always like to have this kind of spring toy. So that's some spring. And then it's like a little sort of toy, so it's got a little face on it, and there it is. Okay, so that's Springy the spring toy. And let me see, what you do with Springy is you kind of put your finger on its nose and you sort of pull it out here, so you sort of stretch it and then you let go. And of course, Springy starts kind of vibrating backwards and forwards. So let's go to the point. So we've sort of stretched him out. There we go. There's Springy stretched out. So that's kind of initial. So we pluck. So at time t equals 0, we're going to pluck Springy to extension x0. So that's going to be the initial extension, and then we're going to let go. Okay, so I'm going to be kind of having x, which is x of t, a function of time. It's going to be the extension of the spring at time t. Right, so measured from the equilibrium point, this is the equilibrium point. There it is. We've stretched it to that initial extension, x equals x0 at time t equals 0. And I want to work out the equation of motion. Okay, so what we need to know for this, we need to know Hooke's law. So that's the law that tells you what force a spring exerts. And Hooke's law says that the force is proportional to the extension. So this is the proportional symbol. A better way of writing it is that force is minus kx, where K is this spring constant. I've put minus because extension is measured positively in this direction, but of course the force is acting backwards in the opposite direction. So you want a negative force. The force is minus kx, and the k is a spring constant here. And that depends on how strong your spring is, right? So a really good spring will have a really high constant K, a big spring constant. But force is just proportional to extension, at least when you're vibrating the spring within a kind of a normal range. So using Hooke's law, then we can so now I can together with Newton's law, F equals ma, we get the differential equation for the motion of the spring. So the force from the spring is going to be accelerating the head of springy. So we're going to get that mass times acceleration. Well, acceleration is the second derivative, x double dot. Mx double dot is going to be minus kx, right? That's F equals ma. So x double dot plus k over mx equals 0. So here is the basic differential equation governing how springy oscillates. And so this is a second order differential equation. And so to find out x, we need to know how to solve that differential equation. Okay, so we've kind of done the physics. We've used Hooke's law and Newton's law, F equals ma, to derive that differential equation, telling us how the extension changes over time. But now we've got to do the math and solve that differential equation to get the formula for x of t. So let me see, I'm going to come back to that differential equation and talk about how to solve that sort of equation there. So I'm going to go over to the next page, and then we're going to come back to this one when we have the kind of the theory in hand to solve this particular type of differential equation. So I guess this is kind of the basic theorem which I'm applying. So it tells you that the general solution of that differential equation, well, so let me go. So this is a general theory. So I'm going to, whereas in the equation I've got on the previous page, I've got function x, which is a function of time. Let me go back to kind of our traditional notation where the variable is not time, but is actually x, and my function is f. And so I'll just kind of go back to the traditional Newton notation. So the second derivative, f double prime of x plus f of x equals 0. So that's essentially the differential equation that I had before, except now I've got f, whereas before I had x, and now I've got x, whereas before I had t, and there's some constant in the equation that I had before, which I've kind of got rid of. There was a constant in there. It would have been that k over m. I'm just assuming it's 1. So for this particular differential equation, which is a very important one, the general solution is that f of x is some constant times cos x plus some constant sine x. And those constants a and b are determined by the initial conditions. In fact, a is just f of 0, the value of the function at x equals 0, and b is just the derivative, f prime of 0. So those would be the initial conditions. That gives you the a and b in that solution. And so I'm going to kind of quickly prove this, just so you kind of see what's going on. So the observation is that both f of x equals cos x and f of x equals sine x, they're both solutions of the differential equation, f double prime of x plus f of x equals 0. Because if you take cos and you differentiate twice, you get minus sine, you get minus cos plus cos, it's 0. If you take sine, when you differentiate twice, you get minus sine plus sine. So they're both solutions of that differential equation. It's what's called a linear homogeneous differential equation. It doesn't really matter what those words mean. I just thought I'd write them down so you've heard those words. Linear means that you've just got the function, its derivative, its second derivative, and so on, just scalar multiples of those things added together on the left-hand side, and homogeneous means you've got a big zero on the right-hand side. Whenever that happens, any linear combination of solutions is also a solution. So I'm sort of trying to kind of sneak in a few words at you here without fully defining them. I just think it's good to kind of get used to these words in an example. Linear combination means something like scalar multiple of one of the solutions plus scalar multiple of the other solution. Okay, so linear combination is when you're kind of doing scalar multiples of the guys and then adding them together. So that's a linear combination of cos x and sin x. Okay, so that checks that this thing here, a cos x plus b sin x, is a solution. Now I'm going to let a be f of 0 and b be f prime of 0. Okay, so we don't know what f of x is, but it's a solution of this differential equation, and I'm going to take the constant a to be what f is at 0 and the constant b to be what f prime is at 0. And I'm going to consider something I'm going to call it g of x, which is f of x, that unknown function that's this solution of this equation, minus a cos x minus b sin x. This is a solution of the differential equation because, well, we're given that f of x is a solution and cos x is a solution and sin x is a solution. So actually this is a linear combination of three solutions. 1 times f of x minus a times cos x minus b times sin x. And this sort of equation, any linear combination of solutions is a solution. So this new function g of x is a solution of this equation. And what's g of 0? Well, let's plug in x equals 0 in here. F of 0, well, f of 0 is a. Cos of 0 is 1, so that's a minus a, so that's all a big 0 so far. And sine of 0 is r. G of 0 is 0. What's g prime of 0? Well, g prime is f prime. Let's put that in little writing here. G prime, it's f prime of x, so I'm differentiating, plus a sine x minus b cos x. And when I plug in 0 in there, that's f prime of 0, which is what I'm calling b. Sine of 0 is 0, cos of 0 is r. It's b minus b. Okay, so this g has these properties. G is a solution of this differential equation, and g of 0 and g prime of 0 are both 0. What I'm going to try and do is show that g of x equals 0 for all x. And once I've done that, if I can show that this g of x, well, that's this stuff here, is just identically 0, I get that f of x minus a cos x minus b sin x is 0, so f of x is a cos x plus b sin x, which is what I'm trying to show, so as required. Okay, so I'm trying to prove this, that's f of x, where a is f of 0 and b is f prime of 0. So if I can show that g of x is 0, that exactly does my job. It shows that f of x is what I'm after. Okay, so all I'm left with doing is proving the claim. To see this, there's a little trick here. You consider the function g prime of x squared plus g of x squared. Let's call that something. Let's call that maybe h of x. So h of x is defined to be g prime squared plus g squared. What's h prime of x? Okay, so I'm looking at this function here. I'm trying to show, okay, I'm gonna take this h, so that's that thing by definition, and I'm gonna differentiate. So I've got to differentiate this, which is power down, it's a chain rule, power down the front, 1 off the power, and then I've got to times by the derivative of the inside. So that's 2 g prime of x, g double prime of x. And I've got to differentiate this. Similarly, that's 2 g prime of x, the derivative of the inside, right? So that's another chain rule, which is 2 g prime of x, g double prime of x, plus g of x. But what's g double prime of x plus g of x? G was a solution of this differential equation, so that's 0. Okay, so this function h of x, this crazy thing I just threw at you, it's a function whose derivative is 0. And we know that if you've got a function whose derivative is 0, then h of x is c, constant. But what's h of 0? Well, h of 0 is that constant, but if we go back to the definition of h of x, h of 0 is g prime of 0 squared plus g of 0 squared. G prime of 0 and g of 0, h of 0 is just 0. So actually, I'm just about done here. This shows that actually h of x is 0 for all x. Right, so now that's showing that this guy here, it's 0 for all x, but this is something squared. Things squared are greater than or equal to 0. This is something squared. Things squared are greater than or equal to 0. The only way these two things can be 0 is if actually g of x and g prime of x is 0 always. And so that checks the claim. And I've proved now that g of x is 0 for all x, hence I've shown that f of x is the gadget I was after. Okay, so maybe that was a little bit too long a proof to give. But I've just proved that the solution of this differential equation, the general solution, has this form, and if you know the initial conditions, you know f of 0 and f prime of 0, then you can find a and b from those two equations. Okay, so that's a very important differential equation. That's why I wanted to go through in detail a first proof of how to solve such differential equations. I guess I kind of used a little trick in that proof. That trick there is a little bit cunning, well, it's because we don't really have any general theory of differential equations in place. Once one does, then this becomes much easier than I've just made it. But we're at the beginning of thinking about differential equations, so we don't have any machines or theory in our hands. So I just kind of gave you a direct kind of simple trick to prove that this is the general solution of the differential equation. It's a second order differential equation, so we were kind of expecting that there were going to be two unknown constants which would be determined by initial conditions, and that's what's going on here. Very good. Okay, so let's go back to our equation that was coming from Springy. So remember, I'm not writing f, I'm writing x, and what was x in that theorem is now time, but this is still that same sort of differential equation. Second derivative, I had plus 1 times x, and now I've got k over m times x, but it doesn't really change anything. When you see this differential equation, you just know that the general solution is a cos, well, t is the variable now, root k over mt plus b sine root k over mt for sum a and b. See theorem below. So it's just of that same nature as what I just did in that general abstract theorem. When you differentiate this guy twice, because it's not t, it's the scalar times t, you use the chain rule twice, and so when you differentiate twice, you get minus k over m times the thing you started with, and then you're adding k over m. So that's a solution, and that's a solution, and it fits the pattern of the general theorem I just proved on the next slide. To find, so now if you set t equals 0, you get that actually a, so when t is 0, that's 0, cos of 0 is 1, so x of 0 is a, but x of 0 is that initial extension, x0. So you get that a is x0, and let's see, the velocity is 0 at that initial moment. When you release the springy at time 0, it's initially not moving. So what's x prime? X prime is the derivative of this thing. So you differentiate cosine, you get sine, but at t equals 0, sine is 0. But when you differentiate this thing, you get root k over mb times cosine of 0, which is 1. But hang on, that's 0. So actually b is 0. Okay, so I was just using the initial conditions to find a and b. So actually x of t is x0 cos root k over mt. And so there, it took me a little while to get there. There is the equation of motion of springy. That's excellent. So we've just solved this kind of very fundamental differential equation. This x double dot plus positive constant times x. And I used initial conditions as well, so that it has this particularly simple form. Okay, so this theorem is this sort of general shape of this type of differential equation. Okay, so let's do some stuff with that. I want to work out how much energy is stored in the spring at that time t equals 0, at that time when it's at that maximum extension. How much energy, how much work did you have to do to stretch the spring to that point? And right, so when springy is at equilibrium, it's not stretched at all. There's no energy stored in the spring, but as you stretch him, you're storing energy in the spring. That's kind of another form of potential energy. And then when you let go of that potential energy, the string contracts, it pulls back. That potential energy it's stored in the spring accelerates it, and it goes into kinetic energy of the head of springy. I should have said all along what m is, so let me just fill that in. M is the mass of the head of springy. And I guess I'm assuming that the mass of the spring itself is negligible. I'm kind of treating this springy as being a point mass concentrated at its head. I was using m all the way through. I didn't say right here what m was. M is the mass of the head of the spring. Okay, so to work out how much energy is stored in the spring, what we could do is we could just think about what's happening. It's at that initial extension, all that potential energy. We can just work out how fast it's going to be going when it gets back to the equilibrium point. That's the point when all that potential energy stored in the spring at time 0 will have converted into a kinetic energy. So this amount of energy that I'm going to want to look at, it's the same as the kinetic energy when it goes through the equilibrium point. Okay, so how are we going to work that out? Well, when does that happen? So I want to know when does it go through the equilibrium point? Well, that's when x of t is 0. So we want this cosine to be 0. So this happens at time. So cosine, we want this to be pi by 2. So cosine 0. So t is So when does it go through the origin? It's when when root k over mt is pi over 2. So t is pi over 2 times root m over k. So that's when it goes through the origin, and x dot of t, well, x dot, if that's x, I can differentiate, right? So I've got to differentiate cosine. I get minus x0 root k over m sine root k over mt. Boy, oh boy. And I've got to plug in this particular value for t in here. And did I differentiate right? Yes, I did. And when you plug that in there, sine of pi by 2 is 1. So that tells me the velocity x dot. I've just run out of room a little bit here. So maybe let's start a new slide. We've just shown that the velocity is minus root, let's copy that, it was minus x0 root k over m when it goes through the equilibrium point. Therefore, the kinetic energy at that point, that's a half mv squared, right, which is a half m. We've just worked out that the v is x0 root k over m. I'm squaring, so I don't really need the sign. So what is that? That's a half. I've got an m, I've got an x0 squared, and I've got a k over m. So I think it's going to be a half k x0. Okay, so that must have been the same as the potential energy stored in the spring when it's at extension x0, because that was right, all that potential energy at time 0, that's been converted into kinetic energy. That was this sort of maximum velocity as it goes through the equilibrium point. So I've used the kinetic energy formula to derive the potential energy stored in the spring. So there it is. That's my final formula. So it's a half k x0, and I had an x0 squared. I'm sorry, I forgot that. And well, there's no real point putting the 0 in there. So this just shows that this argument, it's kind of a bit of a clunky argument. It shows that the potential energy stored in a spring when it's at extension x is a half kx squared, where k is the spring constant. That was a very clunky argument, but I think it got us to practice a few things. Much better would be to use work is force times distance. Right, so a much better way of doing this would be to think, well, okay, so how much energy did we need to put in when we initially plucked springy out to extension x0? That was us exerting a force through a certain distance. But there's a little issue there, right? Because force is minus kx, that's the force in the spring, so we would have been pulling that way, we would have been applying force kx. But the force that we're applying is not constant. Initially, we need basically force 0, and then the more stretched it gets, kx gets bigger and bigger. So the further we stretch it, the more force we need to exert to counteract the force in the spring, to stretch it. So the problem is that I want to use work is force times distance, but the force, kx, is changing as the distance changes. So I can't just do what I did when I was calculating the potential energy, lifting the apple. That was a constant force. But now the force changes as x changes. So the potential energy is going to be... So what I need to take these... So what you have to do is you actually have to integrate. So I mean, it's another perfect situation for an integral, right? So you instead think about stretching this string as stretching it little tiny pieces, delta x. So you're moving it a little tiny distance, delta x, and to move it that little tiny delta x, when you're at extension x, that's roughly then constant, and so you're sort of trying to add up these little tiny increments of work to do each little stretch, and you just pass to the limit as delta x goes to 0, and you get the formula for potential energy, and then it's easy to find an antiderivative, a half kx squared from 0 to x0, which is a half kx0 squared. Again, that matches our formula, and if you're happy to use that integral there, it's a much easier argument than I gave you the first time around. Okay, that's excellent. Let's see if we can do one more thing today. So I gave you F equals ma. So this is kind of Newton's basic law of motion, so this is Newton's law. And I also talked about conservation of energy, and I did a couple of things with conservation of energy and I use work equals force times distance as well. So those are kind of basic techniques in this sort of beginning Newtonian dynamics. Conservation laws are very important at this point. So conservation of energy I've just given you. There's another conservation law which is called conservation of momentum. So a momentum might be a new thing. Momentum by definition is if you have a mass m moving at velocity v, momentum is mass times velocity. Okay, that quantity is called momentum. And actually, Newton's law really says, I think everybody knows F equals ma, that's sort of one of those things you learn at the beginning of physics, but actually it's always kind of stated a little bit wrongly. It should really be this law. It shouldn't be F equals ma, it should be force is rate of change of momentum. That's really what Newton's law says. So v is velocity, and force is rate of change of momentum. So usually what happens is that if m is constant, which it is in a whole load of those sorts of problems that we've been doing, the mass doesn't change over time. And if the m is a constant, you can just bring it out the front of the derivative. So then in that case, the rate of change of momentum is mass times dv by dt, and the rate of change of velocity is acceleration. Okay, so that's the usual Newton's law when mass is constant, F equals ma. But this slightly more general version is sometimes useful. Sometimes the mass is changing over time, and so that's kind of really the right way to state Newton's law. So from that, you have the idea that it takes force to change momentum. If you want to change momentum by a little bit, well, the amount of force you need to do it is it's the change in momentum you want to create. So this is very good. So the upshot of this is that in a closed system with no external forces, if you're looking at a closed system with no external forces, the total momentum in that system must be constant over time. To change the momentum in it, you need to, in your system, you need to apply some external force to create that change in momentum. So that's kind of, I mean, this is where, this is the law of conservation of momentum. So that's kind of the next conservation law that's basic at this point. After conservation of energy is conservation of momentum. If your physical system that you're looking at has no external forces, then the total momentum is just a constant. Momentum is conserved. It takes force to change momentum. And that doesn't mean that when I talked about a closed system, that kind of depends on your perspective, right? So a sort of typical thing that you often see at this point is, you see some particle of mass m and some other particle of mass maybe little m, and these particles collide. So if this first mass is moving at velocity big V, it has momentum m big V. And your second mass might be moving at velocity little v in the other direction, so it's got momentum m little v. And when they collide, these two particles, they'll bounce off each other in different directions. So the left-hand particle, which is going to the right, might bounce back to the left, so they're going to change directions. Now, each individual particle, its momentum changes in that collision, because the other particle exerts a force on it that changes its momentum, and vice versa. But if you treat the two particles together as being a single physical system, then the momentum before and the momentum after must be conserved, because the forces are just internal to the two particles. They're not external forces to the system that's both of them. Sorry if I said that in a confusing way. So it kind of it depends on your perspective. What is the system you're looking at? If you're looking at just one particle, then this collision is some external force acting on that particle that can change its momentum. But if you're looking at both particles at once, then the forces are purely internal to your system, and so the total momentum is conserved. It's very important, by the way, that this velocity would have been a positive velocity, it's moving to the right, and this velocity would have been a negative one. And that sign of your velocity needs to be taken into account. When I write momentum mv, it's velocity, not speed, it's velocity, which is that signed quantity. Okay, I think that's kind of a crash course in some basic physics, which you would definitely have seen if you've taken a first course in physics in high school or something. I'm using a little bit of calculus at the same time, so even in that first course you might not have seen physics with the calculus. On the other hand, if you've taken a proper calculus-based physics course, then this will all be kind of old hat to you, and I'm not saying anything fancy. But I think that's just enough physics. F equals ma, Newton's law, conservation of energy, conservation of momentum. I've derived the formulas for potential energy, when you raise a mass to height h, and potential energy stored in a spring, and I've derived the formula for kinetic energy. So that's kind of just the kind of very basic tools that we need. Now, it's all set up, and in the next lecture, I'm going to start the discussion about planetary motion that we've been working towards for quite a while.